So let's end this lecture with like a quote-unquote application. I like this application because it really it's from 1993. It's due to two people called Elitzur and Vaidman. And this is like a little bit before Shor's factoring algorithm and before Grover's algorithm. But it really, it kind of illustrates this rotation detective idea. And it really arguably kind of presages Grover's algorithm. Although I think Grover might not have been aware of it. So these are two physicists, Elitzur and Vaidman. And they invented like a wacky scenario about a bomb. So it's sometimes called the Elitzur-Vaidman bomb problem. It's kind of weird. Maybe we should like be a bit more chill and imagine it's like a glitter bomb instead of a real bomb. But okay, they invented this crazy problem. So in this problem, maybe you imagine that like you're a supervillain and you have a shtick. Your shtick is like making these weird booby traps that look like this. Okay, there's like an opaque sealed box that has like a tiny slit in it into which could fit like one photon. It's just wide enough. And it has some slit at the outside from which a photon can come out. And inside the box, this is a very wacky scenario. There's one of these like horizontal polarizing filters we talked about last time. And that's like attached to like an extremely sensitive wick. And that's attached to like, you know, a glitter bomb in here. And how does this work? A photon comes in, and like we know this acts as a semi-destructive measurement. And like when the photon comes in at some angle, this either measures it to 0 or has measurement outcome 1. And if like the measurement outcome is 0, horizontal, then it just passes through. Photon goes through, and nothing happens. If the measurement outcome is 1, well, we know that like it gets blocked. And like I also told you, like it turns into like a tiny amount of heat. And then you maybe imagine that like, lights the fuse and then like the bomb goes off. So explosion. Okay, so as a supervillain, you like to make these crazy devices that look like this, which you can fire a photon into and like something might come out, but also it could explode. And by the way, I guess if you fire something into it and you don't explode and something comes out, then the thing that comes out is definitely in state ket 0. Because as we know, like if you make it through this, you collapse to state ket 0. So okay, let's imagine like you're making these like glitter bomb packages, and you've made so many of them, like you're storing them in your attic, and then one day you go up to your attic and you like find one of these boxes, and you're like, oh, I forget whether this is actually, got a bomb in it, or maybe this is just an empty box. Like it still has the slits, but you like forgot if you put the whole apparatus inside it or not. So you're like, maybe this is just an empty box, and it looks like this. Like literally nothing inside. So we'll call this case bomb, and we'll call this case empty. And the task is like, you find this box and you want to know, am I in case bomb or a case empty? And you can already see it's like kind of similar to this, right? There's some sort of mysterious thing. You're promised that it's either like one thing or the other thing, and now we're going to use like quantum to tell the difference. So, okay, you're the supervillain. You're like, I got to remember what case this is. What can you do? So let me start out by thinking of some things you might do that are maybe not so great. And then we'll see a great thing you can do. Okay, so one thing you could do is you could be like, all right, I'm going to chuck in a photon, in state vertical, state ket 1. Now, this is too risky. Like, you would not want to do this. Because if it really is case bomb, if you put it in a 1, then 100% of the time you'll get an explosion. Okay? You'll for sure get an explosion in case bomb. So you're like, okay, that's sad. I shouldn't do that. What if I wanted to put in a horizontally polarized photon? I'll put in like a ket 0. Well, this is kind of pointless. This is truly useless. Because in case empty, what happens? Well, in case empty, anything you put in just comes out unchanged. So ket 0 comes out. And if it's a bomb, well, ket 0 is always just passed through this also unchanged. So ket 0 comes out. And now you could take the photon that comes out and like look at it, but you're like, this is pointless because it's definitely going to be in state ket 0 when it comes out. So like I've literally gained no information at all. So if you didn't know about quantum, or you didn't know that there was more in this world than just horizontally polarized and vertically polarized, you'd be like, I am in like a no-win scenario. If I put in 0, I get no information. If I put in 1, like there's a 100% chance that I'll get an explosion in one of the cases, so I'm completely in trouble. But you can do better than this, and indeed, the very first thing you learn in quantum might suggest, oh, what if I put in like an equal superposition of 0 and 1? What if I put in like ket plus, the 45-degree angle thing? And as we'll see, this is a better idea. It's not the best idea, but it's a better idea. So let's reason this one out. Let's do case empty first. Case empty. Well, in case empty, if you put ket plus in, then just ket plus comes out. Literally nothing happens to it. Okay, let's do the bomb case here. You can think about it in your head what happens in the bomb case. Okay, so case bomb. Well, the first thing that happens is it hits the filter, which is effectively like, measuring in the standard basis. And we know that, okay, this is, if it's perfectly diagonal, there's a 50% chance that it measures to 1. And then you get the bomb. Probability of getting measurement outcome 1, which means an explosion, which is bad. But there's a 50% chance that you don't get an explosion. And in this case, ket 0 comes out. Right? So suppose you cross your fingers, you put like ket plus in, cross your fingers, and something comes out. You didn't explode. You're like, oh, great, phew. So now you're like, okay, given that I didn't explode, either this photon that came out that I grabbed is either ket 0 or it's ket plus. And now you can say like, oh, this is not the greatest thing, but like I do have some ability to tell the difference between ket 0 and ket plus. This is really like this, distinguishing one copy of test. It's either, it's here or it's here. It's 45 degrees. We talked about this. You can do a few things. You can do like the two-sided error algorithm, and the two-sided error algorithm distinguishes ket 0 from ket plus with failure probability like 15%. I think we saw that last time. Or you could, maybe, I don't want to say play it safe, but you can do the one-sided error test. So let's write that. You could do this like 0 versus plus one-sided error test. And you can choose which, side you want to be which. So let's say you do the bomb means bomb version. I don't know if this is false positive or false negative, so let me just say it's this kind. So with false negative, according to my notes, it's false negative. Probability cosine 45 degrees squared, which is a half. Okay, and the nature of this test is that once you do this second test on the photon that comes out, like assuming you don't explode, if it says bomb, okay, if it says not bomb, then it's kind of inconclusive. So 25% chance it says like not bomb, but this is like the error possibility. So there's a 25% chance that like you survive the bomb and you get an inconclusive result. But this is in case bomb. So I'm writing this in a slightly bad way. There's a 25% chance that like overall you survive and you like, detect the bomb with certainty. Hey, let me recap that again just because it's a little bit clear. Let's say it is case bomb. You do this thing where you put ket plus in, and if a photon comes out, then you additionally do this like distinguishing test on it. The final scenarios are, okay, 50% chance you explode. Granted, that's bad. But 25% chance that you survive and you get an inconclusive report. That's not great. But there is like a 25% chance that you both survive and you know for certainty that the thing has a bomb in it. And that's kind of pretty cool. You managed to get into a situation where you know for 100% sure that it is case bomb, and the bomb didn't go off. So that's pretty cool. But now what I want to say is there's something you can do that's even better. At least if you have a bit of time on your hands, there's something you can do that's even better. So this is what you should do, assuming you have a little bit of time on your hands. So I'll write some code here. So first, define a global variable called n, which maybe we'll set to 1,000,000. Let's say it depends on how much time you have. There's eventually going to be like a trade-off between the time you use and the safety you achieve. Okay, so you define this global constant. Then you also define your own algorithm called, I'll call it mystery rotation. Maybe it's like mystery box rotation. I'll just call it mystery rotation. Takes in 1 qubit A, and here's what it does. This is an algorithm that you yourself are designing. First, you yourself will rotate the incoming A by pi over n radians. Then you yourself will take A and put it into the box. Okay, this is a subroutine I'm defining. Okay, so this either causes an explosion, or it spits out, maybe new version of A. Okay. So this is an operation you can do on any qubit A. First thing you do, you rotate it a little bit, and then you put it into the box. That's that subroutine. Now, let's think about what this code is doing in the two possibilities. So in case empty, if the box is empty, then this line literally does nothing. You just put in A and you get back A. So in case empty, mystery rotation, this algorithm that you've defined, is literally equivalent to rotate by pi over n. This instruction is the same as this instruction in the empty case. In the bomb case, it's a bit different. How does this algorithm operate in the bomb case? Well, I'm only going to analyze what happens in the bomb case if you put ket 0 into this algorithm. I'm only going to analyze that case. So if you put ket 0 in for A, well, first thing you do is you rotate it a teeny bit. Okay? So if zero's coming in like horizontal, and you intentionally like make it a little bit rotated, and then you pass it through the box. And so we know since it's like a little bit rotated, the angle is pi over n here, there is some chance it gets measured to vertical and thereby triggers the bomb. That's a very small probability, but it could happen. So if you put in 0, then maybe there's an explosion. But if not, if there's no explosion, like you put in this slightly rotated vector, it hits here, probably it's just going to get measured to measurement outcome horizontal, no explosion, and then it just comes out in state ket 0. But if not, ket 0 comes out. So in case bomb, this algorithm kind of acts like do nothing on input ket 0. It acts like do nothing on input 0, except there's a slight chance of explosion. What is a slight chance of explosion? We saw this. This is like sine pi over n squared, which is about pi over n squared, which is at most 10 over n squared. Okay? So you've cooked it up so that this algorithm, in the bomb case, has this tiny chance of explosion, but otherwise it acts like do nothing on ket 0. And then what do? You just run this algorithm. Just run this same algorithm, except I guess you put empty here, and you put bomb here. And this algorithm is really great, because like what happens? First of all, suppose the box is empty. Then this mystery rotation is rotate by pi over n. And we saw before, in that case, like you just rotate by pi over n over 2 times. It eventually gets to 1. And then 100% of the time, you get measurement outcome 1, you print empty. That's correct. On the other hand, suppose there's really a bomb in here. And you put ket 0 in at the start, which you do. Then, ignoring the possibility you explode for a moment, ignoring the possibility of explosions, all these rotations do nothing. Like it gets 0 comes in, ket 0 comes out. So it's just 0, 0, 0, 0, 0, 0, 0 the whole time. At the end, you extract all, you get 0 for sure, and you print out bomb. So ignoring the possibility of explosions for a second, we have like a much better scenario than this. Ignoring explosions, this algorithm perfectly tells the difference between bomb and empty. The only downside is that there is some slight chance of explosion, but I claim it's really small. In case bomb, what is probability of like any explosion? Well, we kind of did this last time. You can use the union bound again. The chance that you explode is the chance that you explode on time 1, time 2, time 3, times 4, etc. But every time, the chance you explode is at most 10 over n squared. So the chance you explode is at most 10 over n squared plus 10 over n squared plus 10 over n squared, n over 2 times. And that's n over 2 times 10 over n squared, which is 5 over n. And that's really small. If you take n to be 1,000,000, then this is, a 5 in 1,000,000 chance, which is tiny. So sorry for going over time, but the summary is, you define some amount of time you're willing to run for, like n, and then you can perfectly tell the difference between a bomb and an empty box. And the chance of you exploding is like 5 over n. So it's like a time versus safety trade-off. You can make this as low as you want just by investing more time. And the reason it really worked was that this was like 1 over n squared, but this was n. So this quadratic win was what was working for you. OK. I'll see you in office hours later today.